So now that we've talked about iterated integrals, let's talk about area of a plane region. So let's say I'm looking at a region in the XY plane here, and it's going to be bounded above and below by some kind of function here. So maybe this is my g1x, and then I have a top function here, g2x, and x is going to go between a and b. So here's my plane region right here, and I want to find, I'll call this region R right there, and I want to find the area of R. So this is something you looked at before in either Calculus 1 or Calculus 2, and the area of R, I'll call this area A, it's the integral from A to B, and it's top function minus bottom function, so it'll be g2x minus g1x. But we can also view this area as an iterated integral. And why is that true? Well, because if I compute the integral of dy from g1x to g2x, well, I'm integrating 1, which I get y back. And then it's top minus bottom. So this would be g2x minus g1x. So what I can do is I can replace this part here with this integral, and so it becomes an iterated integral. So the area of R is equal to this iterated integral from A to B, g1x, g2x, dy dx. Okay. Well, not all regions in the plane have a top function and a bottom function. Sometimes they're bounded instead on the left and on the right. So what would the picture look like then? Okay, so if I'm in the XY plane now, and now I have a function on the left, call this x equals h1y, and then I have another function on the right, x equals h2y, and then I have some bounds on my y goes from c to d. Maybe this is the region that I'm interested in. This will be my region R. So I'll say that the area of this region can also be viewed as an iterated integral in the following way. R would be the integral, or sorry, the area, I guess A, would be the iterated integral from C to D, h1y, h2y, and then it'll be dx dy. So the order here will have flipped. You're going to integrate with respect to x first, and then with respect to y. But you could find the area using that formula. So now let's look at an example. Let's use an iterated integral to represent the area of the rectangle shown. So the rectangle here goes from A to B and then C to D. Here's my rectangle. So remember on your integration that the outer bounds have to be constant, but here because you have a rectangle, you can use either order. You can't always do this, and in fact usually you can't, but here I have a rectangle which is a very nicely shaped figure, so here I can find it as the integral from A to B, the integral from C to D, dy dx, or you could flip it and then have, if you switch the bounds of integration, you would have dx dy. But here, let's compute this. So the integral, integrate dy, you get y. So this is the integral from A to B of d minus c. D minus c is just a constant. We just don't know what they are, but there's no x there. So when I integrate this, I'll get d minus c times x. And then if you plug in your bounds, you'll get d minus c, b minus a. And this corresponds to our area formula for a rectangle, right? It's the width times the height. So you found it now using an iterated integral.